Okay, now continuing with our commonly used viewpoints, the concurrency viewpoint shows about what are the components that can run together, or those that are concurrently executed. So this is about multi-threaded programming. So as you may know, when you want to create a multi-threaded program using, say, Java or .NET platform, you have to architecture those solutions carefully, right? Because you have to analyze and understand which components or which software, which program components can run without affecting the others, and you have to carefully plan the concurrencies. So concurrency viewpoint is about that. Then there are behavioral viewpoints, how the software behaves for different types of interactions. So the interactions can be from the users, or it can be other components. So when some method call happens, or when a message is received by an by a component, or when the user inputs something, or say something like a mouse click or a button click, okay, how does the system behave to those things? So to those interactions. So the behavioral viewpoint captures the expected behavior of parts of a system. Then we must have consistency among the different views. So these views can contain overlapping and related design decisions. Sometimes the same thing is represented by different viewpoints. So there is the possibility that the views can thus become inconsistent with one another. Now, if different people get involved in creating the different views, right, so then inconsistencies could be introduced. So you have to be careful. So views are consistent if the design decisions they contain are compatible. So if for example, if you have stated that two components can be executed in a multi-threaded environment, but in another, say the behavioral view tells that you need the other to be dependent on the another component which you previously had mentioned in your concurrency view that could be executed in parallel. So then it becomes inconsistent. So that kind of inconsistent views you have to carefully handle. So if the views are inconsistent, two views as a design decisions that cannot simultaneously be true. So one of the two will have to be modified. So inconsistency is usually but not always indicative of problems. Right? So usually it indicates some design problem is there, right? Because normally we look at the design specs or the requirements specifications. So if two different competing requirements are there, then this kind of inconsistencies could be introduced to the models. So for example, temporary inconsistencies are a natural part of exploratory design. So in exploratory design, where you are not sure about how to do something, you design by exploring different ideas. So it is only a temporary thing, right? So once you finalize your design, after identifying all the problems, then the inconsistency will be removed from the design. But then there might be some inconsistencies that cannot always be fixed. So these inconsistencies we have to carefully adjust. We'll have to talk to all the concerned stakeholders. So if it is related to the implementation of a database, they get the database people involved, designers who are designing the database, the programmer involved, right? And if it is something to do with the user interface, UX aspects, okay, get those designers involved, right? So like that, you will have to like talk to all the people before finalizing the model here. So if you look at an example for our lunar lander problem, so we might have a situation like this where we have the ground system sending a signal, and the space link where we have the antenna sending the signals, and there's a command module computer on the ship, and there's a lander computer also, which are connected by a local network link. So in the case, we are saying that our ground system has a system where there is a server side with an IP stack and a space link to connect, and there are middleware connectors, and then there are the components, telemetry, lander monitor, and the ground console systems. Then on the lunar lander side, the client side, the space link connector is there, then the IP stack for the network is there, then the network connectors are there, the middleware bus, and then we have the components, the landing radar, and the SKY control, the thruster control, and other sensors. Right? But when you look at the implemented model, if you compare the ground model and the lunar lander itself, it doesn't match. It doesn't have all the components, that the consoles that are identified in the architectural model. So the physical view that is shown on the left side is the actual one that is now implemented in this lunar lander. So there, it has only 3 hosts: a ground system, a command module computer, and a lander computer. So, however, the deployment view shows components assigned to only 2 hosts. There is only the ground system and a lunar lander. So there's a mismatch. So we call that the inconsistency. So we have to be careful. Whatever you promise to deliver, you must deliver. Right? So it's an architectural inconsistency. So it is fairly easy to see that something is not right here, and there is an inconsistency between the physical and deployment view, and the inconsistency fits the above definition, and the physical view asserts the design decision that lunar lander runs on 2 hosts, while the deployment view asserts the decision that lunar lander runs on 3. Okay, so these kind of inconsistencies we might be able to solve. So there are common types of inconsistencies. Okay, one is the direct inconsistencies. For example, the system runs on 2 hosts and the system runs on 3 hosts. So obviously we can identify there's a problem, and we can just change our model. So because that is the practical thing to do. Then there are refinement inconsistencies. So initially we might like say something, but when you refine, the high level or more detailed model will need to be changed. So the high level or more abstract, and the low level, the more concrete one, which is going to be implemented with the more detailed views of the same part of the system, might have conflicts. In the high level, you might promise something, but when it comes to the details, it will have a different set of details, right? So we call them the refinement inconsistencies. Then there are static versus dynamic aspect inconsistencies. So dynamic means the changing things. So there are dynamic aspects such as the behavioral specification. So how do you handle some exception, or some when user input is given? How do you handle that? Exceptions or problems that are unseen, not planned for problems. So these conflicts might arise with the static aspects. So static aspects, or static diagrams that you have used to express your dynamic aspects, like the state space charts, the state diagrams, or the network topologies. Now in a wireless environment, the network topology might be different. You expect your packets to go in some path, but the actual path might be somewhere else, right? So we cannot always predict how these dynamic aspects will work, right? These are all dependent. So sometimes we are unable to exactly model the static diagrams of dynamic aspects. Then there are dynamic versus dynamic aspect inconsistencies. Now, as we mentioned earlier, when we say dynamic here, it's about the always changing values or the aspects of the system, right? So there are dynamic aspect inconsistencies versus the static or the dynamic diagrams. So there are different descriptions of dynamic aspects of a system conflict. So you might show different descriptions of a dynamic aspect in a diagram, whereas the actual dynamic aspect is something else, right? So the dynamic diagram shows something which is different to the actual dynamic aspect, right? So that we call the dynamic versus the dynamic aspect inconsistencies. Then there might be functional versus non-functional inconsistencies. So most of the time we are easily able to identify the functional requirements and include them in our models easily. But when it comes to the non-functional requirements, depicting the non-functional requirements with like we need to specify the adjectives, the adverbs that qualify our non-functional requirement. So describing those things in a given notation, architectural model notation, is sometimes difficult. So because of that, sometimes only the functional part is included in the notation, the architectural model notation. It depends on the notations. Right? So say if you take the tier and layer diagram of a system, if you just mention the functionality, and if it does not say something like, say, completing a transaction within, say, 30 seconds, something like that. So that time limit, how can you include that in a tier and layer diagram? There is no way to include it in a graphical way. So you will have to include the annotations. So a lot of non-functional requirements need to be annotated. It has to be textually, you have to describe. So sometimes you forget, right? In cases where you are not being rigorous, and when very formal documentation is not needed, the non-functional requirements are not correctly documented. So that is another inconsistency. Then when you want to evaluate the modeling approaches, you have to consider the scope and the purpose. So you have to carefully think, what does the technique help you model, right? And what does it not help you model? So if you take something that is closer to your heart, something like, say, UML, what can UML help you model, right? So if you draw a use case diagram, a class diagram, say activity diagrams, so those aspects you can clearly depict using a UML model. So you know the scope and the purpose, why you are doing it, right? And you have to also identify the limits. What does it not help you model? So a lot of the non-functional things will not be shown in the graphical part of the UML diagrams. And the basic elements, what are the basic elements? What is the smallest thing that you can show in that notation? And then how are they modeled? Right? So you can say, if you take a class diagram, what is the smallest thing that you can draw in a class diagram? So you might have the class name, the method, the parameters, right? So the variable values. But can you go to the level of the implementation detail? No, right? Most of the time, you have a limit to the basic element, the smallest part that you can include in the model. So you have to identify the smallest part, the basic element that you can show in the model. And then the style, to what extent does the approach help you model elements of the underlying architectural style? So remember last week we talked about the styles. So we have to follow the given style. Once you have decided on a particular architectural style, your architectural models should adhere to the architectural style, right? So to what extent does this approach help you model the underlying architectural style? And is the technique bound to one particular style or family of styles? Sometimes, say UML is very universal. So there are some UML diagrams you can include in any of the architectural styles. But some particular diagrams you only require for certain types of architectural styles. Say for example, if you are following a domain-specific software architecture, say for banking, and you need to highlight on the security aspects, then the UML might not be enough. Right? Then you might need some specialized diagram that shows the vulnerabilities of the system and how the that gives the descriptions about how the firewalls are set up, how the antivirus software has been set up. So all those details will be needed that are not provided in a universal notation like the UML. Then there are again the static and dynamic aspects, right? So what static and dynamic aspects of an architecture does the approach help you model? Now, normally static models that are included in the UML will not show the real dynamic aspects. So if you are really interested in showing how the dynamic aspects are evolving or changing in real time, you will need some special simulation software to be used, right? If that is the case, so then the architecture will need to include that tool. Then when it comes to dynamic modeling, to what extent does the approach support models that change as the system executes? So the approach that you select, the notation or the simulation software that you are using now to model your dynamic model, how real is it? So is it able to show the real-time situation, or does it have a time lag? So that kind of things are also important if you are like gonna base your model for decision making. Then the non-functional aspects. To what extent does the approach support or explicit modeling of non-functional aspects of the architecture? So we have to be careful about the level of detail of the non-functional aspects of the model.